All right, so our next speaker is Samuel, and he's going to talk about sustainable development. Thank you.
All right. Welcome, everyone, to my talk on sustainable development of stencil-based HPC applications. So I'm Sam from CSCS, ETH Zurich, and here are my co-authors. In HPC, the challenge that we have is the same since a while and will be for a while, right? Scalable performance, performance portability, productivity. Basically the main response to this challenge from us is to do automatic shared and distributed memory parallelization and optimization of architecture agnostic code. And to do that, we create HPC building blocks because I strongly believe that the challenge needs to be split up into manageable tasks, where the demanding computer science tasks are then largely solved in such building blocks. And our building blocks are instantiated in these packages. I will give you, in my talk, a quick overview of these packages, and then afterwards explain our approach, meaning also these packages on code examples, and then give results and conclusions. Overview of this building blocks. Well, first, we have certain requirements that come from our projects, right? Here, this GPU4Geo project. A big amount of requirements. So they're always, it's different to just do something without thinking about the real-world applications, or then really try to do it in a way that it can be used in practice. In general, ParallelStencil and the other packs, what they do, ParallelStencil is hardware agnostic. It allows to write hardware agnostic kernels in mass close notation or explicit, and automatically optimize it, optimize code, stencil-like or other code. And stencil-like here is really the widest possible sense, basically relative indexing with respect to a thread ID. Implicit global grid is distributed parallelization, and CellArrays for GPU-optimized logical arrays of arrays of structs. Now, what is new? Or more newish, let's say, we have AMD GPU support for all of this. And now in ParallelStencil, we have code generation of polyester code in order to multi-thread, which is in particular efficient for small problems. And also we fully use and embrace the Julia extension feature. So I quickly show you here how that it could look like. So we have first CUDA extensions, the module, right, when you create an extension, an AMD GPU extension and the package. And each would just initialize ParallelStencil with the corresponding backend. And then what's particularly, then the code that we would include here can be shared. It doesn't have to be different. And ParallelStencil generates, in the end, just regular CUDA code or any GPU code. And so, of course, to create an extension is just the usual way, right? Just remember or think that init ParallelStencil is to be called just each time in each module after using ParallelStencil. So it basically gives you the flavor of the module. Now, to give an explanation of the approach in this code examples, we have a very high-level way of writing things, very mass close. You see here Fourier's law of heat conduction, conservation of energy, update of temperature, really nearly written as you would write equations. And what is particularly important to see here, the fluxes and dt is not stored in memory, because you see in the signature of the function it doesn't appear, so it will automatically be done on the fly. Also, one can use other macros. You can define them yourself, right? Then that was the kernel, right? And in addition to that, of course, we need to have some allocation of arrays and then call our kernels, and that's what we see here. And what we have in particular here is we have this feature hide communication in order to overlap the computation with the communication. And so what happens in general is we compute the boundary regions and inner points on different streams, and as soon as the boundary region is finished, we start the Halo update. And then, of course, that is runnable on a single CPU core or on thousands of GPUs. Now I will just do a quick dive into the hiding of communication, how that looks like. So if things go wrong, if you, for example, here put a synchronization after each call, then you will have these gaps here and nothing overlaps. And you can see here, just to understand what's going on here, in blue there, in the Halo communication part, you see what is written into GPU buffers, and the like brownish part is actually the transfer from CPU from the GPU buffers to the CPU, and through the network. Then this is all done by the GPU-aware MPI. And so the network communication is not visible, but would also be there. I see that the time seems to be up. I only have 7 minutes on my chronometer, so I need to go a little bit further. Sorry. Then you see here, if things go right now, how it goes. We have boundary region computations on the left, and then the overlap of the inner point computation with the Halo computations. And nice to see here is that the boundary region computation, if you zoom in, they also overlap partly. And actually that means that when the kernel has not anymore enough blocks to saturate the GPU, then the next kernel already starts and can that way saturate the GPU at all time. Now this here would show how it works when we don't have GPU-aware MPI available. And so what's nice to see here is that it basically looks the same way. You see these little blocks are about the same size as before, and there we also have these brown things there, and one is highlighted in yellow, and this, if you look at the bottom right, you see we have a throughput of 2.9 gigabyte per second, which is basically the peak performance of the PCI Express that we have on PitStained. And so the result is we get a similar performance as with GPU-aware MPI. Now we can also, when we have multiple arrays, we can overlap these different arrays in the data transfers. And I will try to speed up now very much, so we can do many more things which we have talked about already in the past, like automatic differentiation, etc. We have also logic arrays of arrays, which I've only mentioned. I will not go further in detail now. And we have a magic flag to do memory optimization. And this, the results of that I have shown already in last year's talk. Check that out. Scalable 3D PD solvers tackling hardware limits. So there we could show that we really get very close to the peak and get a significant speed up over explicit CUDA or KA. Then we have some quick scaling results here. It's like 93% for diffusion and 96 for real-world applications. Here we have on Lumi the diffusion, and here a real-world application about 96%. That is all. Thank you very much.
Thank you. Very nice result. Actually, I also used PStance at some point. So yeah, it's very nice to see that there's a continual improvement on performance. All right. Any quick question? If not, I just want to ask a very brief one. What's the geological application you're trying to solve?
One of them is ice sheet flow, which has been presented in other talks, with fast ice, etc.
Okay. All right. Thank you.